Hi, welcome to Teardown Tuesday. Yes, it's vintage time again, and we've got not vintage computer, but vintage microprocessor development tool. We've got a Microtek 8086 in-circuit emulator or ICE tool, and we'll take a good look at it in detail. I scored this baby on eBay for 99 cents. I was the only bidder. Fantastic. Came in the original box with all the original manuals, all the original cables, all the pods and ZIF sockets and everything. Beauty. Can't believe it. And yep, check it out. There it is. This is the 8086, but this particular unit supports the 8088 processor and the NEC equivalents, the V20 and the V30 as well. If you remember, the 8086 or the 8088 was what was used in the original IBM PC back in the early 80s, and that's what all modern Intel, Wintel type PCs are based on. And this was an incredibly valuable development tool back then. If you were developing a PC or hardware for a PC, something like that, you really, or even software, you really needed one of these in-circuit emulators or ICE. Now, as you'll see later, I'll show you the real thing, but it basically is a box like this, which we've seen, cables coming out, we've got pods which then go off and plug into the socket on your processor. Now, you might think that, well, these aren't used anymore, but, well, they effectively still are. An in-circuit emulator is the penultimate tool for embedded system design and embedded computer, software debugging, hardware debugging, stuff like that. And you might be familiar with, say, the PitKit 3, microcontroller debug tools. These are not in-circuit emulators. These are in-circuit debuggers or ICDs, and they work differently because these are what are known as intrusive debuggers. That means that you have to actually put code into your PIC chip or your AVR chip when you're actually developing it to, to debug and breakpoint and stop and look at stuff and play with it and debug it. And well, that's not your final code. These things do not, these in-circuit debuggers do not allow you to debug your final code. And that's important. And that's where these in-circuit emulators, they might be called emulators. They go under various names, but they're generally known as an ICE or an in-circuit emulator. That's where these come in. These are non-intrusive. These emulate the actual processor, so they've got specific hardware in here and they emulate the whole chip. They're very complex things to actually design, and hence they're very expensive. And well, back then in the day, they were very big as well. There'll be a lot of circuitry in here, which we'll take a look at. Now, in-circuit emulators are still used today, but they're generally still quite an expensive and rare tool to have, but absolutely essential when you want to do non-intrusive debugging on a design. There is no substitute for it really. On microprocessor-based systems that have separate memory and the processor, separate I/O chips and separate memory, really old school stuff instead of the embedded micro processors and microcontrollers we have these days. You could use a logic analyzer or something like that. That's another non-intrusive technique to debug your applications, but they're not the best. You cannot beat an in-circuit emulator that allows you to monitor your code real time, trace your code in real time, see exactly which part of your C program's executing, all that sort of stuff, break into it, breakpoints, do your usual debugging stuff on your actual release code. And that's a vital part of it. So anyway, I think these things, this is going to be really, well, it's going to be interesting inside, but unfortunately, I'm not going to be able to power the sucker up because, well, it comes with a plug-in ISA bus card for a PC. I don't actually have the original software for this either, and I don't have an 8086 target system to play with either. But hey, we'll take it apart and see what's inside. I expect a whole bunch of through-hole 80s technology. Let's go. Now I'll just expand on this in-circuit commentary a little bit more. Here's a pretty old, you'll notice the date code there, 9804 PIC 16C74A micro controller, but you know, it's a typical, still a fairly typical microcontroller these days, and everything is built into this thing. All of the memory, all of the I/O and UARTs, and you know, various other stuff are all built into there. And how do you emulate this thing? Well, you can emulate it using a a dedicated hardware that actually emulates the chip, but you always wonder, well, how accurate is that? And of course, we can't get in there to actually probe any of the signals normally if we use the regular chip. Like, we can't break into the memory and simulate it, and well, you know, program the memory, trace it, examine the contents, put contents in there, do all that sort of jazz, because in fact the ROM memory in this one is UV erasable. It's not a flash memory, hence why it has this clear window on top. You have to actually erase this thing under ultraviolet light. Well, in-circuit emulators, they work differently. Even if you've got a flash-based controller, in-circuit emulators will generally use RAM memory, fast volatile memory, to simulate the flash or the ROM memory in a system. So you don't have to wait for the flash memory to be programmed or something. You can just do it very quickly, almost instantaneously, in static memory. So how would you actually probe into a system like this to do this? Well, you have to actually rely on the manufacturer, and manufacturers still manufacture these days, I believe, but back in the old days they definitely did it all the time. They would manufacture a special version of the chip called a bond out chip, and what it does is it actually, instead of all the regular pins on there, it bonds out extra wires out to extra pins, which are then able to tap all the internal parts of the circuitry, like the memory and you know, all sorts of other peripherals and various important points within the microprocessor. You can break those out and then use that special, very expensive chip usually to develop an in-circuit emulator, so it emulates the real chip. But often with these bond out chips, they would lag behind the real production versions of the chips. If there's silicon bugs and the production chips are being fixed, well, whoops, you know, your in-circuit emulator using that bond out chip could be out of date, and it was always a struggle to keep up with these things using bond out chips. But yeah, the manufacturers would actually manufacture a special version of this chip. They didn't make many of them because these in-circuit emulators don't sell in, you know, the tens of thousands or hundreds of thousands like the little, you know, pick kit debuggers and stuff do these days. These were very expensive, very specialized chips. And of course, as you might be aware, a lot of modern microcontrollers have built-in sort of, you know, in-circuit emulator and in-circuit debugger type functionality already built into the production die. That's why, say, you know, on the microchip you can use the in-circuit debugger, which actually has some circuitry already built into the die that allows you to do basic breakpoints and basic debugging, stuff like that. And for those who love to see the original boxes, I've got all the original foam inserts in there. I've got the Universal Symbolic Debugger User's Manual, as well as the original disc for the Symbolic Debugger. Fantastic stuff. I've got all the connecting ribbon cables for the things. I've got the pods, of course, which we'll take a look at, complete with the original, hopefully, all the pins intact. All the pins intact. Fantastic. That plugs into your circuit under test with your ZIF sockets. I've got, actually, there's a couple of those. They're both for the 8086, and it supports the 8087 as well. There's the emulation microprocessor. Fantastic stuff. And comes with the original ISA control board as well. Copyright 1986 Microtek, although I think this actual unit is about, well, the manual says 89 or thereabouts, so, but it could have certainly been manufactured in the very early 90s, and various other connecting leads as well. There, that's the trace pin output leads. So, oh, yep, go into some micro grabbers down in there. I've even got the warranty card. Fantastic. And a whole bunch of stuff. Brilliant. All for there's a third. There you go. I've got a third pod which doesn't have the 8087. It's only got the 8086 socket in it. So here's how the thing would hook up. You would have your ISA PC card running the emulation software, which allows you to do all the on-screen displays, the waveforms, the debugging, the whole works, and all the timing stuff. And that would plug in and connects to the cable on the back, which we'll have a look at. And then you would plug these lovely long ribbon cables here. There we go. This one's specific for the 8086F. I'm not sure what different cable would be for the 8088, for example, but these would plug into there like that. Bingo, there you go. And then you would plug your actual microprocessor that you wanted to emulate into here, and your 8087 as well if you were using the 8087. And then this cable would connect into your circuit under test. It would plug into your microprocessor socket. So instead of this processor plugging directly into the socket like normal, you would put all this circuitry and this in-circuit emulator or ICE in between it. Now this is actually not so much an emulator, because it's not actually emulating the microprocessor. The circuitry inside this thing is not emulating the microprocessor. It's using a real microprocessor, and it's tapping into that and just tapping into all the memory signals and the clock signals and everything else required to run the PC, because the processor is just that. It's just a processor. It needs all external memory and everything else. So that's why you could do this with the 8086, which you couldn't do, for example, on that PIC we saw earlier. You would have had to use a bond out version of the chip. Now this is using the real microprocessor, of course, is much better than using a circuitry that is like a PLD or an FPGA that's just emulating your microprocessor, because then you don't know if there's any bugs or any issues with your emulation at all. You don't know if it's 100%, but when you're using your real actual production silicon in there, you can be 100% sure it's a true emulation. Now, one of the issues with in-circuit emulators, which is still true today, you can't get around it, it's basic physics, are the speed limitations. Now, when you're talking about big cables like this, which break into your circuit under test, look at all this. These signals have to be broken out, go into here, all through the circuitry in here, all through these huge cables in here, all to the circuitry inside this box, and that is a lot of extra copper. Yeah, remember that signals travel at roughly, rule of thumb, 15 centimeters per nanosecond. So every 15 centimeters on this cable is going to represent a 1 nanosecond delay. And well, that can be a huge problem if you're working at a processor, pretty much in a system like this with the connecting cables and stuff like that. Once you start talking 3 digits or 100 megahertz, these types of systems aren't really going to work anymore. So this one's only working at 10 megahertz maximum, because that was the upper speed of the 8086 back then. So these types of systems with the long cables and breaking into it all worked just a treat. But on modern processors working at many hundreds of megahertz, in-circuit emulator design is a real art in itself, and trying to minimize the physical interconnections for various things, even for bond out chips and stuff like that. You have to be very careful. Signal integrity becomes a huge deal, and flight time on the copper cables or any interconnects at all can really ruin your day. It really is quite a difficult art to design these in-circuit emulators. Huge R&D dollars go into these things, and they don't sell many of them, so they're usually pretty darn expensive. And that's the reason why they've put the emulation microprocessor as close as physically possible to the connection pins here, is because they really need to keep that signal integrity as best they can. If this emulation microprocessor was inside this box and had to go through all these huge long cables to get there, which is a physical requirement, this box can't be inches away from your system, your device under test, or your DUT. It can't be several inches. You've got to have all these buffered cables, so there'll all be all buffer circuitry and stuff inside here to drive all these long cables. and also to drive out to the socket here, but that's why that's physically kept as close as possible. And on the newer higher speed systems today with, you know, processors with many hundreds of megahertz, you know, you won't even get this distance. You'll, you know, only get maybe an inch, or the circuitry has to be built in to clips which specifically go onto the processor, or they have to build it onto the die. So although this thing is called an in-circuit emulator, it's not actually emulating the microprocessor. It's using the real silicon, your real production silicon, plug it in there, and it just breaks out everything around it, allowing you to do full in-circuit emulator capability, like memory mapping and stuff like that. Now let's take a quick look at the manual here for those who want to see it. Unfortunately, it didn't come with the software like it did the 5¼ inch floppy we got with the debugger software, but anyway, well, what the heck. Third edition, January 1989 there. So really, we are talking, but it could have been manufactured, you know, early 90s or something like that. Originally copyright 86. Microtek International, all rights reserved. And let's have a look at some basic specs of this puppy, and blah 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 blah. Maybe I'll no, I haven't got time to scan any of this, sorry, too hard. I was going to, but it allows you to emulate 8086's 8088, 8087 coprocessor, the NEC V20 and V30, goes up to 10 megahertz external clock. The emulation memory is important. That's the amount of static RAM built in, as I mentioned, because even with, you know, modern systems with flash program memory and stuff like that, you know, they've got a limited write cycle, limited life in them. So really, static RAM just allows you to do infinite and also pretty much instant changing of the emulation program memory. Now it's only got 256K, so I'm not sure what you'd be doing if you had, like, if you were debugging or emulating a 640K system, for example. I'm not sure if you can probably bank it or do something like that, up to 464K segments. It's got 7 real-time breakpoints, 4 execution breakpoints, and 2 bus breakpoints, which allow you to get you know, various things, because there's a lot of hardware that's actually required to do that. So that's why you can't just have an infinite number of complex. These are often called complex breakpoints. So it taps into the address, data, status, and some counts as well. And it can do interrupt, IO read, and stuff, all that sort of breakpoint stuff. And it's got 1 external hardware breakpoint as well. And it does real-time tracing of the address, data, all the rest of it. The trace buffer is only 2K and 76 bits wide. What else we got? Register. You can display, modify. You can single step. You can single step through, and the time measurement has a resolution of 1 microsecond. You can do cycle steps, trace start stop, all the memory commands you can do, and the various interfaces. So there you go. That is a basic introduction. If there's anything more interesting, I haven't actually read it yet, but here we go. Here's the system block diagram. It tells us what cards we've got in here. We've got our LAM card. I'm not sure what that was. The top card is called the EPM card. The middle one is called the EMM, and the bottom one is the next one down is the LAM card, and then we've got a CPM card. So it looks like we've got 4 boards in this thing, and they're all going to, I'm sure that'll all be dip and through hole technology, and we'll open up the pod as well. But the pod, I only expect to see buffers and things like that, perhaps. Bingo, there we go. We've got logic. LAM is logic analyzer module. EMM is emulation memory module, so that was a separate board, and the CPM is the control processor module. And a quick look at the front, we've got a 5-volt power LED. Everything's going to be 5 volts, no 3.3 volt rubbish in this thing. The emulation program run, I assume that's what EP stands for. Green LED, green is good, your program's running. It's got various sync outputs, master and slave, external trigger input, and your trace outputs as well, which you can connect to your circuit under test. And then we've got our pod interfaces here, and we've got a funky little recessed reset button. And that's all there is to the front of it. And On the back here, we've got a parallel and serial interface, which goes off to our board. We've got a fan and just IEC mains input. That's it. Made in Taiwan, Republic of China. All right, what was that, like 10-15 minutes of crapping on about in-circuit emulators and stuff like that? Let's have a look inside this thing. Now, as I said, I reckon it's going to be all through-hole technology. Oh, bugger. We need a... let's have a look. Is that a... that's a hex. We need a hex. Nope. Loser. There we go. Do it by hand. There we go. We will find, no doubt, a whole bunch of through-hole circuitry all dip stuff. I mentioned this on the Amp Hour radio show this morning. Actually, I presume that all the chips will be lined up. Like, you can sort of see through the grills on the front a bit, but all the chips will be lined up there in their lines. There'll be through-hole packages, and it'll all be jammed on there. I'm sure probably like a 4-layer board, each one of them, or something like that. Oh, does that come out? No. All right, looks like we have to... there we go. And we've got 4 boards, as we saw in the manual. So not a hugely interesting teardown. I mean, you know, the more interesting stuff in this is actually how, like, maybe the circuitry of how the emulation worked and stuff like that. So you have to really go into, there we go, deep technical ta-da! Yep, there we go. Exactly as I thought. So there you have it. There's the 4 boards we saw before. Nice little retaining clips to pull them out. I'll have to undo the screws there, but on the top here is our emulation programming board. Then we've got our emulation memory module next, and then we've got our logic analyzer module there, which of course has the various trace bits and stuff like that on it. And then down the bottom is our emulation processor, our CPM, control processor module. So there you go. Let's undo the screws on here and whip this sucker out. Gonna have to... I've used a hex driver here, but this is how you designed... Oops. Oh, no, it doesn't like that. Oh, no. Maybe I'm using the wrong... Maybe it's Imperial. I don't have an Imperial that small. Damn it. Bugger. I think someone may have had a hack at those, because this one worked, these two over here work fine, but the other ones don't. Anyway, I'm sure we can get those off with a pair of pliers. Anyway, this is how you designed stuff back then. No large scale integrate. Well, there's large scale integration in you know, various 40-pin dips and stuff, but everything else is going to be either gate array logic or 7/4 series logic, and this is how you laid stuff out, and this is how you designed stuff back in the day. You know, you didn't have... oh, well, you had FPGAs and stuff like that if you wanted to use them, or you had PLDs and stuff anyway that you could certainly use, and those gate array logics, I can probably see, I think I see maybe some gate arrays on there or something like that. So, but you design these all in neat rows like that, and then you would typically have, as we'll see on the board, you typically had all the traces on one layer going in one direction, and on the other layer going all the other direction, and that's one of the good uses for auto routers back in the day. In the CAD software, you would let the auto router rip. So you'd lay it out, you'd put a bit of sense and order into the layout, of course, but you'd lay them out all nice and neat like that with their individual bypass caps on each chip, and then you'd tell the auto router, go for it, and you'd come back, you know, come back at the end of the day, and your board would be done. So I can get a couple of those out. No, they're probably held in at the back as well, so I'm not sure what's... no, there we go, we've got one out. Oh, that's neat. I like it. So we'll have a look at each board in a bit more detail. It's got a daughter board on it. Oh no, there we go. Just takes a bit of force to pop out. Ta-da! That's our logic analyzer module. And these ones, I'll have to get those out with a pair of pliers. And here it is. And this is a classic example of how you would design something back in the mid to late 80s. You would have, you know, a whole bunch of 7.4 series logic. This is the emulation memory board, of course, the EMM, and you would lay them all out on boards like that, and you'd plug them into a backplane rack-based system like this, because you've got all this circuitry which you obviously can't fit on one board. There's no, you know, huge large-scale integration and stuff like that, so you lay them out on multiple boards, and very common to lay them out on these with these backplane bus connectors. You know, you'd see almost every system back in the day, every sort of you know, processor system that did all sorts of logic stuff like this would be pretty much designed exactly the same way, either a horizontal plug-in system like this or a vertical rack format one or something like that. But yeah, classic old school. So this here is the EMM, or the emulation memory module. There it is, they call it the HEMM Rev D, copyright 1989. Just have a look at 92, there you go, 9235 on a couple of these. Just have a look at the date code of a few of these chips, 9224. So it looks like this one was manufactured late 92. There you go, that dates this thing, but it was certainly designed back in 1989. It would have had, you know, probably a 5-year lifetime or something like that before people moved on. But this one actually comes from the Australian Air Force, so you know, they have to maintain these old systems. So you know, there'd be probably still some people, you know, running these old tools even today, because they still have to emulate the old, you know, the old microprocessors like the 8086 and various others. You know, if you're working on, say, ICBM technology for the military, intercontinental ballistic missiles, they're all based on, you know, 60s technology and stuff like that. So, you know, they still have to keep alive these development tools, and that can be a big challenge in itself, to maintaining old systems like that, especially in military type things where you have to keep things working for, you know, 10, 20, even 30 years or so. Crazy stuff. It can get real difficult, so, you know, don't throw out those old floppy disks. And you can see the classic card edge release clips like that. Absolutely classic. I can remember designing many a board back in the day to slot in there. We've got a metal strengthening bar across here. You'll notice that it's probably held in, yeah, it's held in 3 locations. So there, there, and there, and that just strengthens the board at the back as it plugged in, because when these, you know, on really big boards, they could actually sag in the middle. So when you actually went, a common issue back in the day is when you put them in the slide rails like that and you pushed them in, sometimes there'd be a lot of weight on these things, especially if they're, you know, I've done boards like, you know, double this size almost, and in the middle they can actually sag like that if they don't have one of these strengthening bars, and then the connectors at the back like this don't line up, so that can be an issue. So that's why they've added that metal strengthening bar on the back, just to keep it all lined up when you go to plug it in. Although these connectors are pretty good, it's pretty, you know, self-aligning, all that sort of stuff, but you really didn't want to hear that big crunch sound as they sort of self-aligned when you pushed them in. But there you go, attention to detail. Now, as I mentioned, this is a classic layout for a board of the era. This would be a 4-layer board. You can actually see by the dark bits in there, it's actually a well, it's at least a 4-layer board. They wouldn't have done it as a 3-layer. Of course, there'd be ground and power in there, so 2 inner layers, and there'd probably be very little, few if any traces on the inner layer. It would just be the power plane, and all of the routing is done on the top and the bottom layer. And as I said, this was a classic use for auto routers back in the day. You know how I'm not a big fan of auto routers. Well, this is where they came in handy, because these weren't huge, you know, high frequency systems. These are only, you know, 10 megahertz, 20 megahertz, something like that, with a big ground plane, lots of decoupling. You can easily get away with, well, you had to get away with it because you had to make these systems work. You had to use all these chips, spread them out over large boards like this with backplanes, but signal integrity wasn't, on the PCB level, wasn't as huge a thing as it is today with all of today's you know, high-speed serial lines, controlled impedance and all that sort of stuff. These things weren't controlled impedance. You just laid it out with one big ground plane. You'll notice they've got decoupling chips on each one, but you'll notice how they're all laid out in nice lines like this. You would lay them out like that, and typically this is not a good example of that one, but this isn't a particularly good example either. This is the processor, the emulation processor module, but they're laid out in neat lines like that. And if you didn't have the ground plane, often they would run the ground and power trace between each chip like that and run it across the board. So you'd have one big power bus down the side, and then you'd branch the power off along each particular chip like that, especially if you had multi-voltages or something like that. You typically might have a different voltage bus on each side or something like that, and you would route them under the chips. That's why you line them up like that, so that you could run those two traces, ground and power. That's the only thing you'd have running under the chip in that direction like that, and you dedicate a particular layer to that direction of running all of those power signals. But they obviously haven't done that here. They've just used a one big power plane. It's all running at 5 volts, ground and power in there, but each chip they've given a bypass cap on each one, but they've still laid them out in neat rows like that, because the routing algorithms, you would, I don't know if this one was auto routed or not, may or may not be. I've both used auto routers and laid out these types of ones manually as well. We'll flip it over and have a look, but as I mentioned back at the start, these things, they're typically will dedicate one particular layer to a direction. So this bottom layer here, you'll notice almost all of the traces go in this direction, this x-axis direction here. There's a few traces which sort of, come down here like that and then go, oh, I'm going to go down there like that. But generally, the routing algorithms were quite advanced, and they were optimized for these two-layer boards. In fact, the CAD packages these days will probably still have the algorithms built in, and you tell it that I want to run my traces in that direction on this layer, and on the top layer you run them in the other direction there. So here it is. All the ones on the top here pretty much all just run in this direction like this, and this is why you can't just put your chips anywhere willy-nilly. You have to actually especially with memory and stuff like this, this is all banked, all common address and data lines, so you're going to put them in right aligned all the way up like that, and the buses just run directly through them like that. And absolute classic example of how to lay out one of these 4-layer 1980s vintage digital boards. So of course you did have to put some thought into the layout of this thing, component placement. As I've always said, PCB layout is 90% component placement. You do good placement, the auto routing routines can work just fine. And of course, if you had to get a signal from here right over there, you didn't care how, it might jump across on the bottom layer here, jump up, back there, back. It'll just, as it's easy to find a route when you first start laying out the traces, but when you get to that 90% routing mark, and well, you haven't got much room left, you really have to jump all over the shop here. But this one is quite efficient. I mean, it's probably put a lot of thought into it and laid it out by hand, because you can't see too many vias in there. There's a couple, there's a few, but there's not like, hundreds and hundreds of vias and stuff like that. So they really, I'd say somebody has probably manually routed this thing and took some pride, but for some complex ones where the signal integrity isn't critical, yeah, just let the auto router rip on these boards. It's fun to watch. And check out the ancient bypass capacitor package there. They've got standard 0.3-inch spacing on these things, designed to integrate and butt right up next to chips for high density, in quote marks, logic designs like this one. Absolute classic. You don't see packages like that anymore. I'm not even sure if you'd still be able to get that sort of package. And of course we've got a tantalum here as well, in one of these weird ass bullet type packages. Okay, let's start out and look at each board in a little bit more detail, look at some of the technology that's used on here. This is the top board we looked at, the EPM, or the Emulation Programming Module, and you can see this one is where it connects directly to the pod using this dual height riser IDC connector like that. It's rather quite neat. You know, nothing fancy there at all. It's just a 40-way levered IDC connector. We've got a couple of dip resistor networks here, series resistor networks. I'm presuming that they're I don't know. Yeah, I think they're series resistor networks there. And then we've got some 7.4 stuff around here. It's all a lot of this is going to be standard 7.4 logic. So if you want to know what each one of them does, by all means go and look up the individual data sheets if you're not familiar with your 7.4 series logic. But anyway, they're using LS series logic for presumably around the interface stuff here. We've got some ALS, so we're really going to have a mix of 7.4 series technology here. I have no idea what these Sony parts are here. Check it out. Sony CXK 5814P. Well, of course, the dash 35 on the end of that's a dead giveaway. That's some type of memory, and I did Google it, and sure enough, it is a 2K by 8 SRAM. So very fast SRAM there on the input. Then we go down here and we find 7.4F series logic. So we've moved, F stands for fast, folks, and they are incredibly fast. They take a lot of current as well, so you really need a bypass cap next to each one of those. So, and these ones with stickers on them, there's a couple of them there and up there as well. They would be gate arrays, like a PAL device or a gate array or something like that, because when they've got a serial number on them like that, you can bet your bottom dollar that they're programmable. So let's peel that off, and oh damn, can't see it. One of those difficult to read ones. Let me try and get in there. Yep, there you go. It's a PAL. It's not even a GAL. It's a PAL 16 R8. Absolute classic. They're just using that for some glue logic there. And if we have a look around the rest of the board here, LS123 up there with some large traditional radial caps there, but pretty much 7.4F series as far as the eye can see, pretty much in terms of you know, where it's deemed to be critical speed. There we go. We've got a Cypress CY7C122. Once again, it's a -15, so that would be a memory. I'm not going to bother to go look that one up. You can do that yourself. All 7.4F series logic driving the backplane down in there, and of course each one of those has to have its own bypass cap because those things just gulp the current. But it looks like 7.4 with the, we did have a ALS up here. Where was it? Yep, there we go. So we've got a small mix of different technology there. They've chosen to use two 7.4 ALS ones there instead of LS or F in that particular circumstance. Looks like somehow coupled into that memory. And down here we've got the classic, it's an NEC branded, but lots of companies made this. It's the classic 8255 programmable peripheral interface, and this was used on the IBM PC and standardized in part, you know, the Intel architectures and stuff like that, but they're just using it as a, I think they've just standardized. They've got 4 of them here. They've just standardized on those as their 8-bit peripheral, addressable peripheral bus interface. I won't go into detail on how the 8255 works if you're not familiar with it. I'll link in the data sheet to it and you can check it out. It's just a generic way for them to address and read stuff on data bus based systems. And there's the main clock up there, 24 megahertz crystal oscillator, and that's pretty much all she wrote. So it looks like we've got 3 combinations of family on there. F predominantly, LS second, and then ALS as well. And next up we've got our emulation memory module, which contains all the mapping memory in here. Once again, they've got some GAL or PAL stuff happening down in there, but these are all Sony CXK 58257 70 nanosecond SRAMs. Are more than fast enough for a 10 10 megahertz emulation system. They decided to go with 70 nanoseconds there. Pretty bog standard. You could have substituted these with, you know, any one of dozens of brands available at the time. And what was that? It had 256K total. So there you go. Once again, they've got all 74F series logic, or driving that. I guess they determined that LS wasn't fast enough for any of that. All, you know, classic 245s and 244s and all sorts of stuff all over the place. Yeah, there's some more 244s, and once again they're throwing in just a couple of ALS, a little bank of ALS ones going down here, and there is another. I'm not sure what that one there is. Once again, it's another memory. It's of sorts. It's got a -15, so anytime you see like a -15 on the end, especially in this old stuff, you can pretty much tell that that's a speed grade, and that will be usually -15 means, well, that could mean 15 nanoseconds, or it could mean 150 depending on the technology. -70 here, I definitely know from experience, would be 70 nanoseconds, but might try and Google that sucker. I'm not sure who that manufacturer is offhand. Well, there you go. That one is from a company called Pyramid Semiconductor. I'm not sure if they're still around these days, but yes, it is a small SRAM. Yes, it is 15 nanoseconds. Very quick. It's 256 bits times 4, so it's, you know, it's incredibly small. I'm not sure what they're using that for. Just some sort of little smaller buffer or fast counter or something like that, perhaps. But here you go. We've got our 8255s again, so that's all our generic interface stuff. 74Fs all over the place, 4 8255s, and another memory down the bottom there. But yeah, I know, what can I tell you? Sorry folks, it's all just 74 series logic. And here's our LAM, or logic analyzer module. Once again, that's these are the trace outputs here, and the various sync and trigger inputs here. But this is the logic analyzer module that allows them. Oh, there we go. MPower LAM. Once again, we've got a. Oh, actually, that. Wonder who or what that is under there. Just curious, because that looked like a National Semiconductor, and it is. There you go. It's a PAL 14. PAL 14L4. Woohoo! State-of-the-art technology, folks. In the late 80s, no FPGAs in this baby, and looks like, yep, 8255s absolutely everywhere, in bucket loads all over. Once again, we've got some more of those 2K SRAMs there, I think, and yep, a whole bunch. There we go. Whole line of them. In fact, a whole line of SRAMs on the logic analyzer module. And if we look at the manual, we should be able to find that is like the probably the trace buffer or something like that. And yep, I was right. This is the trace buffer memory along here, because the manual, as we saw earlier in the video, the manual states that it's got 2K 2048 cycles deep by 76 bits wide trace memory. Of course, these are all 8 bits each, so in theory you need 9.5 of these chips to make up that trace memory, but they've got more than that. These are 2K by 8 each, so they've got 2, 4, 6, 8, 10, 12, 14, 15, and they've got another one there, 16, but I don't know how they're being used and implemented. But definitely the trace buffer, and a slightly different mix of technology again, 74S 260. So we've got 74S series logic mixed in with our LS and our F all around there. And we've got an NEC D71054C, not sure what that is, could be another memory, doesn't have a dash grade after that. Once again, these are all late week 91 sort of manufacturers, so yep, 9223. So there you go, we've got some more Sony 2K memory SRAM there all over the place. But yeah, well, we've got a LED, something different. And last but not least, we have our CPM board. No, it's not a control program for microcomputers, as in the CPM operating system. It is the control processor module. And ta-da! We actually have something different in a genuine I might add. Check it out. Genuine 3M text tool socket there. Beautiful. I like that. What do we have? We have an Intel, ta-da, 80186. Now, there's actually no reason that I know of why this actually needs to be an 80186. It doesn't need to be that particular type to emulate this processor, because it's not doing emulation, it's just doing control, basically. So that could have been any processor. They just happened to use an 80186. They probably use the same thing for their emulators for other brand microcontrollers as well, not the 808, 8086. So there you go, there's our system ROMs there. So this just, you know, it's the main control processor. It's right into all those 8255 programmable peripheral interface chips on the various other boards. And you'll notice that the all of the traces on there, they've gone all a bit willy-nilly in there. Look at that. But anyway, I'm not sure what that puppy is there, X2212P. It looks like some sort of custom branded thing. I'm not entirely sure what that thing is, but yeah, once again, some 74LS series stuff surrounding that. The main clock is 16 megahertz for that system. They've got some memory there, and looky down here, we have a Zilog SCC, or Serial Communications Controller. I love it. Copyright 1981. Thing's ancient, but they were still manufacturing it more than a decade later in 92. Go figures. And that's running from a 3.68640 megahertz crystal. Why that particular frequency, I hear you ask? Well, it's very common because that is a direct multiple of the serial UART interface. So if you punch that in, 3.68640 on your calculator, and divide it by a typical UART baud rate, say 19,200, you'll get an exact binary multiple. So you can get an exact frequency, and that's why they use that oddball frequency crystal there. It is quite common. But apart from that, folks, that is all she wrote on there. Sorry, it's not terribly exciting at all. There's a bottom board on there, but it doesn't look like there's anything interesting. Just a few passives and some resistor networks for the serial and parallel interfaces there. But I suspect there'll be a lot of annoyed people if I don't just pop open this 3M text tool socket here. So here's the bar, and hey, there we go. Ta-da! And there's our, what is that, like an LCC? Something like that. There it is. Look at that. Gold. Ah, thing of beauty and a joy forever. And for those keen to see inside the power supply, I don't like to include power supply stuff. We've been looking at all this digital, but nice change of pace. Look at this. Very neatly laid out, quite sparse. There we go. The main controller down there is a TL494, absolute classic, and very neatly laid out. Heat sunk over here. You can see the sill pads on the transistors over there, along there. This is like a couple hundred watts. Well, I think this thing takes like 100 watts total or something. It takes a hell of a lot. But they've actually gone to a bit of effort. Look, they've folded this case in here, which has the voltage selection switch on the back here, which protrudes from the back. The cable runs all the way down to the bottom down here. Looks like we have some MOV protection. There's the main bridge rectifier. These are the two high voltage caps. A couple of main switching transformers, but yeah, it's a power supply. And let's just have a quick look inside the emulation pod here. It just one of them was actually damaged, and there is actually a difference here between, this is just the 8086 on its own. You'll notice it's got more circuitry around here, lack of relays. There's a bodged part up in there. I'm not sure what that sucker is. We'll have to take a good look at there, but you can note the nice 3M text tool sockets. Lovely. I mean, I got this whole thing for 99 cents. You've got to be kidding me. But the one with the 8087 doesn't have nearly as much circuitry around here, and it's got 3 relays up here on the top. So I don't know, they're probably switching power or doing something else. Not quite sure what. Resistor network down in there, but yeah, it's basically 74 ALS 244s, 74 ALS 257s, and you know, pretty much they're only just basically doing buffering on this board pretty much. There we go, 245s, 244s. So, yep, nothing particularly special. Oh, we've got a ULN 2003A transistor driver there. So they'd probably be driving the relays actually, because the other board, probably you won't find that. ULN 2003 Classic. Oh no, sorry, there's a little relay there. What am I talking about? No, you don't really find it. It's got some extra circuitry. So there are some differences between these two modules, certainly. So there you have it. That's a look at the Microtek MICE or MICE-16 8086F in-circuit emulator. Absolutely classic. At first, well, I'm not sure this particular model, but their first model came out in 1981, according to their website. They're still around, Microtek, and this is still all they do. They do in-circuit emulators, but you know, there doesn't seem to be much on their product page. Still looks like they focus on like Intel and one or two other architectures. So there you go. Go figure. If anyone has any further info on this thing, especially schematics or service manuals or anything like that, or heck, even if you work at Microtek still, please let us know. Jump on over to the EEVblog forum and discuss it. And I'll whack in some high-res photos as always. Usually for my teardowns, I also take some high-res photos as well, and they will be on my Flickr account website, which is always linked in down below and on the website. So, hope you enjoyed that bit of retro development in-circuit emulator technology. Brilliant. Classic 1980s. Catch you next time.